Okay, how about we finish that last question that I didn't finish on my last video, if you're watching these in order. But even if you aren't, let's go over it real quickly. Equilibrium. We're given an equilibrium constant. We're given an initial amount of H2 and an initial amount of F2. It's in a 1 liter flask, so 2 moles per 1 liter, 3 moles per 1 liter, 2 molar H2 and 3 molar F2. But we're not given anything else. All we have to guide is the constant, 220, for the concentration constant. Again, if I'm given nothing else, if I'm not given any equilibrium concentrations, why in the world wouldn't you measure that? But you can predict what would happen even if you didn't have the any concentrations, because you can say that this is going to go down, this is going to go down, and this is going to go up. There's none of that, so it's going to go up. And if this side goes up, both of those sides both of the reactants on the other side have to go down. So this goes down, this goes down. These both go down by the same amount. Call that X and call that X. This goes down by X. They both go down by X. But since there's a 2 there, I better call this increasing twice as fast as those are decreasing, or twice as much, and twice as fast, actually, as those are decreasing. Call them X and 2X. But then, of course, we don't know what X is. That's part of the definition, part of the utility of algebra, I guess. 2 minus X and 3 minus X, but here I have 0 plus 2X, which gives 2X. And I do little, like I mentioned on my last video, I should call that F. I don't know where this note ever came from or went to, but it's a typo. So change that to an F, F2. So F2 and H2 go in the denominator. The HF goes in the numerator squared. 220 must equal that ratio. And I don't know what X is. So I FOILed this and multiplied this times 220 on both sides and distribute the 220 into that quadratic and bring the x squared terms over to the same side and set it equal to 0. That's math. Lord. So this looks like a parabola if you were to graph it. And the question is, where does the parabola cross the x-axis? And those are the solutions, or the roots, to this quadratic. Honestly, if I'm just doing this as homework or practice, there's an app for this. It's like a quadratic equation solver. And I just type in the A term and the B term and the C term, and it spits out a couple answers for me. But on the test, we might be really mean and ask you to use one of these, where I go back to junior high and say, oh yeah, I think I was told this equation. The negative of b plus or minus the square root of b squared minus 4ac divided by 2a. And the plus or minus means it could be plus or minus. So here's the plus part and here's the minus part. Don't you just love algebra? Mathematics is a very useful tool. So I get 2 answers. How can there be 2 answers to x? Well, mathematically it's quite possible, but chemically one has meaning and one doesn't have meaning. Well, it has some meaning, but it's nonsense. Sometimes one will come out to be negative, one will be positive. In that case, the negative one is certainly not the answer. But in this case, they both came out to be positive. This one's almost 2, this is a little more than 3. One way I decide which one's legit is I go back up to my definition and say, could x be 2 or could x be a little bit more than 3? Well, I said almost 2, didn't I? Could x be almost 2, a little bit shy of 2? Could x be a little bit shy of 2? Could x be a little bit shy of 2? Yes, I think it could be. Could x be 3? What's 2 minus 3? 3 something. That'd be negative something. So x being 3.1-ish or 3.2 is too big. Therefore, I'm using my logic reasoning skills to say that this one's too big. So my answer for x must be 1.94. Well, I shouldn't just be proud of what I did there. I should take it, the 1.94, and plug it back into my ICE table and figure out my ending concentrations. 2 minus 1.94, 3 minus 1.94, and 2 times 1.94 give me these molar concentrations. So this went down, this went down, this went up, and then I take those and plug them back into the law of mass action. I see I must have come up with I'm doing kind of a check here. This should come out to be 220. I must have rounded these numbers off too much somewhere. But if I do that, then these concentrations should give me, according to the law of mass action for this particular equation, that 220 value. That was so much fun. You could try one if you want. You could pause the video. Here's an equilibrium equation. tells me the constant is 2, just a little bit more than 1, so maybe a little bit of this is favored. Um, do I have 8 waters? 1, 2, 3, 4, 5, 6, 7, 8, and 6 carbon monoxides. 1, 2, 3, 4, 5, 6. 6 carbon monoxides. Oh yeah, so I have 6 of these and 8 of these. And all I know is the constant. And I'm supposed to find out how many of the molecules of H2 and CO and H2 and CO2 are present at equilibrium. Well, I'm pretty sure I'm going to need an ice table. So I start off with 8 of these and 6 of these. They don't mention having any of that in the beginning, so it must be 0. But if I have none of these in the beginning, then of course they're going to want to go up. That's what that arrow says. Chemistry says this one and this one want to react this way to give a little bit of that and a little bit of that. So these will go up a little bit and these will come down a little bit. But that little bit, I don't know. This one's nice because it's just stoichiometry, a balanced equation, 1 and 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 1. These go down by 1x, these go up by 1x, 0 plus x, 0 plus x, 6 minus x, 8 minus x. That's the tricky part. Well, it's tricky, it's the chemistry part. Now comes the math part. So I'll put an x and an x for these two upstairs. I'll put 8 minus x and 6 minus x downstairs. Looks like I have to FOIL that, and the constant is 2, so I'll multiply this times both sides to shift it over to the 2 side, distribute the 2 into the parentheses, and shift the x squared from this side over this side to come up with your final quadratic expression. Then this one's luckily, interestingly, probably factorable or something, because the solutions came out to be, if you go, what is it, negative b plus or minus, oh, I forgot already. I'm embarrassed. I never use it. There's an app for that, but I should practice. Negative b plus or minus the square root of b squared minus 4ac. Did you practice that in junior high? Did you have nightmares about it? Did your parents help you over the dinner table with the math homework? Oh man, that was a long time ago. Alright. Anyways, you solve the what could x be so as to allow this to equal 0, or graph it on the graphing calculator, but you can't use the graphing calculator on the midterms or the finals. So anyways, yeah, yick. I think you're actually given the quadratic formula on the third midterm. What midterm are we on? I don't know. So the answers are 4 and 24, but of course 24 is too big because 6 minus 24, 8 minus 24 would give negative concentrations. Can't have such a thing. So 8 minus 4 gives you 2. 6 minus 8 minus 4 gives you 4. 6 minus 4 gives you 2, and this is 2, and this is 2. Interesting. That was just a stupid clicker thing. You can ignore that. One more example. New equilibrium expression. Ozone O3 plus nitrogen monoxide in equilibrium with, what is that, O2 and NO2. Oh, there it is, duh. Ozone plus NO. Alright, so what am I told? In a 3-liter vessel, the following initial amounts are injected. So 3 liters, so how about 9 moles per 3 liters? That's 3 molar, and 9 moles per 3 liters. That gives 3 molar as well. I think I need an ice table. So there we go. 9 moles in 3 liters, that's 3 molar. None of this and none of this was mentioned in the beginning. Oh, actually they mentioned that we had none. So these are both going to want to go up. These are both want to go down. But by how much I don't know. It's a 1 to 1 to 1 to 1. That's kind of convenient. Maybe we should practice some of these without the ones there, right? The constant is 25, so it tends to say that I'm going to probably still in the end to have more of this than this, but I'm still going to want to generate some of that. So 3 minus x and 3 minus x in the upstairs, x and x in the downstairs. By the way, sometimes these equilibrium problems can end up with cubics or fourth power. What is that called? Polynomial. It's just ridiculous to solve those, so we won't do any of those. But oh, here's a trick. Check this out. So in the numerator, I had 3 minus x and 3 minus x, and in the bottom I had x and x. So this is 3 minus x quantity squared and x quantity squared. But you know what? How about if I just take the square root of this and the square root of this? Take the square root of this side and the square goes away. Take the square root of this and you get 5. And therefore, 5. So bring this x over to the 5 side. 5x equals 3 minus x. add an x to both sides, 6x equals 3x equals a half. So I guess this goes down to 0.5. No, this goes up to 0.5. This goes up to 0.5. This goes down to 2.5. This goes down to 2.5. 2.5 times 2.5 over zero point 0.5, and 0.5 should be 25. I hope. You can check that if you want. Ooh, did I go too fast? I need a drink of water. See you soon. Thanks for